Light travels at 299,792 kilometers per second. That number is worth pausing on because we throw around the phrase speed of light without truly appreciating what it means. At that velocity, you could circle the entire Earth 7.5 times in the span of a single heartbeat. You could travel from New York to London in about 18 milliseconds, faster than you could blink. You could reach the moon in 1.3 seconds, Mars in 3 minutes, Jupiter in about 40 minutes. If someone on the moon sent you a text message and you replied instantly, the entire round-trip conversation would take less than 3 seconds. Light is fast. Light is, as far as the laws of physics allow, the fastest anything can move through space, not the fastest anything has ever moved. The fastest anything can ever move. Einstein's special theory of relativity, confirmed by over a century of increasingly precise experiments, establishes this as a fundamental property of the universe. The speed of light is not just a big number. It is a cosmic speed limit, hardwired into the fabric of space-time itself. So here is the question. If you could somehow travel at that impossible speed, the absolute maximum velocity permitted by the laws of physics, how long would it take to escape the Milky Way galaxy? The answer depends entirely on which direction you choose to run. And the difference between the fastest route and the slowest is not subtle. It is staggering. Our galaxy is not a sphere. This is the first thing you need to understand, and it is the key to everything that follows. The Milky Way is a disk, a vast flat pinwheel of stars roughly 100,000 light-years across, but only about 1,000 light-years thick in our neighborhood. The proportions are extreme, far more extreme than most people realize. If you scaled the galaxy down so its diameter matched a standard dinner plate, about 25 centimeters across, the thickness would be only about 1/4 millimeter. Thinner than a credit card. You would need a magnifying glass to see it edge on. The Milky Way is less like a ball and more like a compact disk, or maybe a fried egg with a bulge in the middle where the yolk would be. This shape has profound implications for escape. If you head straight up, perpendicular to the plane of the galaxy, punching through the thin layer of stars above us, you could escape the densest part of the Milky Way in about 1,000 years. A millennium at light speed. That is roughly 40 human generations watching the stars thin out around them, the familiar constellations stretching and distorting as relativistic effects take hold, until finally the last stragglers of the galactic disk fall behind and nothing but the void of intergalactic space stretches ahead. 1,000 years sounds like a long time, and it is. It is longer than the entire history of the English language, longer than the gap between now and the Norman conquest, longer than the lifespan of most civilizations. But compared to the alternative routes out of the galaxy, it is a shortcut, a cosmic fire escape. If you head toward the center of the galaxy or outward toward the rim, the journey takes 25 to 30 times longer. The galactic center lies about 26,000 light-years away from Earth. The outer edge of the visible disk sits roughly the same distance in the opposite direction. Either way, you are looking at a journey measured not in millennia, but in tens of thousands of years. Let me put that in perspective. 26,000 years ago, the last ice age was in full swing. Glaciers a mile thick covered most of Canada and northern Europe. Humans had not yet invented agriculture, or writing, or cities. We were small bands of hunter-gatherers, chipping stone tools and painting animals on cave walls. The oldest known cave paintings in Europe date to about 36,000 years ago. The domestication of dogs was still thousands of years in the future. Everything that has happened since then, every empire that has risen and fallen, every book that has been written, every war that has been fought, every scientific discovery, every work of art, the entire span of human civilization fits into the time it would take to reach the galactic center at light speed. And here is the part that really bends your mind. Even after tens of thousands of years at light speed, you would not have truly escaped the Milky Way. Not completely, because the visible disk of stars is only part of the story. Our galaxy is surrounded by an enormous halo of dark matter, invisible to telescopes but gravitationally dominant, extending nearly 1 million light-years from the galactic center. This halo contains no stars we can see, no planets, no nebulae, nothing but the invisible scaffolding of matter that holds the galaxy together. To fully escape the Milky Way's gravitational embrace, to reach a point where our galaxy no longer has any meaningful pull on you, you would need to cross this dark frontier, a journey that would take almost 1 million years, even at the speed of light. But before we explore these escape routes in detail, we need to understand how we figured out the size of our galaxy in the first place, because that story is almost as remarkable as the distances themselves. It spans 2 centuries of painstaking observation, revolutionary insights, bitter controversies, and occasional blind alleys. And it is a story that, in many ways, is still being written today. For most of human history, nobody had any idea how big the Milky Way was. Nobody even knew what it was. The band of pale light stretching across the night sky was a mystery, explained variously as the path of souls traveling to the afterlife, the milk of a goddess spilled across the heavens, the backbone of the night, the road to the palace of the gods. The ancient Greeks called it Galaxias Kyklos, the Milky Circle, which eventually gave us both the word galaxy and the name Milky Way. The Romans called it Via Lactea, the road of milk. Different cultures saw different things in it, dragons and rivers and cosmic serpents, but all agreed it was something celestial and mysterious and utterly beyond human understanding. The first breakthrough came in 1610, when Galileo Galilei pointed his newly constructed telescope at the Milky Way. What he saw astonished him. The pale glow resolved into countless individual stars, far more than the eye could see unaided. The Milky Way was not a continuous band of light or a celestial river or the road to heaven. It was stars, millions upon millions of them, packed so densely that their light blurred together into that familiar pale band. Galileo published this discovery in his Sidereus Nuncius, the Starry Messenger, one of the most revolutionary scientific documents ever written. But while he could reveal that the Milky Way consisted of stars, he could not measure how far away those stars were, or how many there truly were, or what shape they formed. Those questions would take another 3 centuries to answer, and the answers would overturn everything we thought we knew about our place in the universe. The first serious attempt to map the Milky Way came from William Herschel in 1785. Herschel was a remarkable figure, a German-born musician who moved to England and became one of the greatest astronomers of his age. He had been a professional oboist and composer before developing a passion for astronomy in his 30s. Unable to afford the telescopes available commercially, he taught himself to grind and polish mirrors by hand, eventually building instruments that surpassed anything else in the world. Herschel's method for mapping the galaxy was simple but clever. He called it stargazing. He would point his telescope at different parts of the sky and carefully count all the stars he could see in his field of view. Then he would move to an adjacent patch of sky and count again, and again, and again. The logic was straightforward. More stars in a given direction meant the galaxy extended farther that way. Fewer stars meant you were looking toward an edge. If you were standing in the middle of a forest and counted trees in every direction, you would count more trees when looking along the length of the forest, and fewer when looking toward a nearby edge. Herschel applied this same principle to stars. After counting stars in over 600 different directions, a project that took years of painstaking work, Herschel produced a map. It showed a flattened, irregular, lens-shaped collection of stars with the Sun sitting roughly in the center. The galaxy, by his estimate, extended perhaps 1,500 light-years in its longest dimension and perhaps 300 light-years thick. Herschel's map was wrong. Not just a little wrong, catastrophically wrong. The actual galaxy is nearly 100 times larger than he estimated, and the Sun is nowhere near the center. But the errors were not Herschel's fault. His method was actually quite clever for its time. The problem was an invisible enemy he did not know existed: interstellar dust. The space between stars is not empty. It is filled with gas and dust, hydrogen atoms and tiny particles of carbon and silicates, thin enough to be invisible to casual observation, but thick enough to dim and redden the light from distant stars. A cubic centimeter of interstellar space might contain only a single atom, vastly emptier than the best vacuum we can create in a laboratory. But over distances of thousands of light years, those sparse particles add up. When Herschel counted stars, he was not seeing to the true edge of the galaxy. He was seeing only as far as the dust would allow. Beyond a certain distance, typically a few thousand light years, stars simply vanished from view, their light absorbed and scattered by the intervening particles. Herschel thought he was seeing the edge of the galaxy. He was actually seeing the limits of visibility through a dusty haze. It was as if he was standing in a fog and concluded the world ended at the point where the fog became opaque. The fog did not mark the edge of anything real. It marked the limit of how far he could see. This same problem plagued every astronomer who tried to map the galaxy for the next century and a half. The dust created a false edge in every direction, making the galaxy appear smaller and more centered on the Sun than it actually was. Jacobus Kapteyn, a Dutch astronomer working in the early 20th century, produced the most elaborate model yet. He coordinated observations from over 40 observatories worldwide, compiling an unprecedented database of stellar positions, brightnesses, and motions. He developed sophisticated statistical techniques to analyze the data. His model, published in 1922, showed a galaxy about 40,000 light-years across, with the Sun located just 2,000 light-years from the center. The Kapteyn universe, as it came to be called, was a masterpiece of careful science. It represented the state of the art in galactic astronomy, and it was fundamentally wrong. For the same reason Herschel's map was wrong. The dust created false edges that Kapteyn could not see through, no matter how sophisticated his analysis. The breakthrough that would finally reveal the true size and structure of the Milky Way came from an unexpected direction, literally. Harlow Shapley was a young American astronomer working at Mount Wilson Observatory in California during the 19-teens. He had an unusual background for a scientist of his era. He had grown up in rural Missouri with little formal education, working as a crime reporter for a local newspaper before deciding to attend college. He arrived at the University of Missouri intending to study journalism, but the journalism school was not yet open, so he flipped through the course catalog and chose the first subject alphabetically: astronomy. It was a decision that would change our understanding of the universe. By 1915, Shapley was working with the 60-inch telescope at Mount Wilson, then one of the largest in the world. He was studying globular clusters, those ancient spherical swarms containing hundreds of thousands of stars, gravitationally bound together in tight balls about 100 to 300 light-years across. They are among the oldest objects in the galaxy, fossils from the universe's early star-forming epoch over 10 billion years ago. About 160 of them are known to orbit the Milky Way. Shapley noticed something peculiar about their distribution. Globular clusters were not scattered evenly across the sky. Instead, they clustered heavily in one direction, toward the constellation Sagittarius. About a third of all known globular clusters appeared in just 2% of the sky. This asymmetry demanded explanation. Shapley reasoned as follows: the globular clusters must form a roughly spherical halo around the galaxy's center. That was the only configuration that made gravitational sense. A spherical halo centered on the Sun would appear evenly distributed, but if the Sun were off to one side of the galaxy, the clusters would bunch up in the direction of the true center. To test this idea, Shapley needed to measure the distances to globular clusters. This was no easy task. The clusters were far too distant for parallax measurements, the technique of measuring how much a star appears to shift against the background as Earth moves around the Sun. Parallax works well for stars within a few hundred light-years, but the globular clusters were much, much farther away. Fortunately, a tool had recently become available, and it came from the work of a woman who never received the credit she deserved during her lifetime, despite making one of the most important discoveries in the history of astronomy. Henrietta Swan Leavitt was born in Massachusetts in 1868, the daughter of a congregational minister. She attended Oberlin College and later what would become Radcliffe, where she took a course in astronomy that sparked a lifelong fascination with the stars. After graduating, she volunteered at Harvard College Observatory, eventually joining the staff as one of the Harvard Computers, a group of women hired to perform the tedious mathematical work that male astronomers considered beneath their dignity. The women were paid 25 to 50 cents an hour, far less than male employees doing similar work. They were not permitted to use the observatory's telescope themselves. They could not attend faculty meetings or publish papers under their own names without special permission, but they could analyze the photographic plates that the telescope produced, measuring star positions and brightnesses and cataloging the results. It was grunt work by the standards of the time. But it was also an opportunity. The Harvard computers had access to more astronomical data than almost anyone else on Earth, and Henrietta Leavitt had the intelligence to see what that data was telling her. Her assignment was to catalogue variable stars, stars whose brightness changes over time. She was specifically studying a type called Cepheid variables. These are pulsating stars that brighten and dim in a regular rhythm, like cosmic heartbeats. Different Cepheids have different periods, ranging from about a day to several months. Leavitt was analyzing Cepheids in the small Magellanic Cloud, a satellite galaxy of the Milky Way visible from the southern hemisphere. This choice of target turned out to be crucial, because all the stars in the small Magellanic Cloud are at roughly the same distance from Earth, about 200,000 light-years. Any differences in their apparent brightness must reflect true differences in their intrinsic luminosity. The distance factor was held constant, allowing true stellar properties to emerge from the data. And Leavitt noticed something remarkable. The brighter Cepheids pulsed more slowly than the dimmer ones. This was not a vague correlation. It was a precise mathematical relationship. When she plotted the periods against the apparent magnitudes, the points fell along a clear line. If you knew how long it took a Cepheid to complete one pulse, you could predict exactly how bright it truly was. Not approximately, exactly. Leavitt published this discovery in 1912 in a short paper in the Harvard College Observatory Circular. The paper was barely 2 pages long and was signed by Edward Pickering, the observatory director, with Leavitt credited only as having prepared the results. This was standard practice at the time. Women's contributions were routinely minimized, but the implications were profound. The period luminosity relationship, as it came to be called, provided a cosmic yardstick. If you could identify a Cepheid variable star anywhere in the universe and measure its pulsation period, you could calculate its true brightness. Compare that to how bright it appeared through your telescope, and simple mathematics would give you its distance. The dimmer it appeared relative to its true brightness, the farther away it must be. Every measurement of galactic and extragalactic distances for the next century would trace back to Henrietta Leavitt's careful analysis. She died of cancer in 1921, at age 53. Just as astronomers were beginning to appreciate the full significance of her work, she never received a Nobel Prize, though the Swedish mathematician Gösta Mittag-Leffler tried to nominate her in 1926, only to learn she had been dead for 5 years. Nobel Prizes cannot be awarded posthumously. Shapley seized on this tool. He searched for Cepheid variables in globular clusters, found them, measured their periods, calculated their true brightnesses, compared those to their apparent brightnesses, and computed distances. The results were shocking. The globular clusters were not a few thousand light-years away, as the Captain universe would have suggested. They were tens of thousands of light-years distant. Some were over 100,000 light-years away, and they formed a spherical halo centered not on the Sun, but on a point in the constellation Sagittarius, roughly 50,000 light-years distant. In one stroke, Shapley demolished the conventional picture of the galaxy. The Sun was not at the center. It was not even close. We were peripheral residents, orbiting far out in the galactic suburbs, while the true center lay tens of thousands of light years away, invisible to optical telescopes because of the intervening dust. Shapley announced his results in a series of papers between 1918 and 1920. The galaxy he described was vastly larger than anyone had imagined, roughly 300,000 light years across. His specific numbers were off by about a factor of 2 due to calibration errors in his Cepheid measurements and his ignorance of how interstellar dust affected his observations. Modern values place the galactic center at about 26,000 light-years from Earth, not 50,000. But the essential insight was correct and revolutionary. The Sun is not at the center of the galaxy. We occupy no special place. We are not privileged observers at the heart of things. We are ordinary residents of an ordinary suburb in one arm of a vast spiral structure. This was the astronomical equivalent of the Copernican revolution. Just as Copernicus had removed Earth from the center of the solar system, Shapley removed the Sun from the center of the galaxy. Both discoveries told the same humbling story. We are not at the center of anything. We just happen to think we were, because we could not see far enough to know better. While Shapley was revolutionizing our understanding of the Milky Way's size, another controversy was brewing about what lay beyond it. Astronomers had long puzzled over the spiral nebulae, those fuzzy spiral-shaped smudges visible through telescopes. There were thousands of them scattered across the sky, and they came in many forms: tight spirals and loose spirals, seen face-on and edge-on. But what were they? Were they nearby gas clouds within our galaxy, perhaps protoplanetary systems in the process of forming? Or were they distant island universes, separate galaxies comparable to our own, located at tremendous distances? This question had been debated for decades, but by the 1910s, it had reached a crisis point. The observational evidence was ambiguous. Some astronomers pointed to novae observed in spiral nebula. If these were ordinary novae, similar to those seen in our own galaxy, then the spirals must be extremely distant. But others argued that the novae in spiral nebulae were abnormally bright, suggesting the spirals were relatively nearby. On April 26, 1920, the debate came to a head in a public confrontation that has gone down in history as the Great Debate. The venue was the Smithsonian Institution in Washington, D.C. The occasion was the annual meeting of the National Academy of Sciences. The combatants were Harlow Shapley, fresh from his revolutionary work on globular clusters, and Heber Curtis, an astronomer from Lick Observatory in California. Shapley argued that the Milky Way was essentially the entire universe, or at least the entire significant portion of it. His evidence was the enormous size of the galaxy he had recently established. The Milky Way was not a modest system of a few thousand light years. It was a vast structure, hundreds of thousands of light years across. Given such enormity, Shapley reasoned, there was no need to invoke external systems. The spiral nebulae must be relatively nearby gas clouds within our own galaxy, perhaps protoplanetary systems, or some other local phenomenon. Curtis argued the opposite. The Milky Way was large, yes, but not infinite. The spiral nebula were not gas clouds, but island universes, separate galaxies comparable to our own, located at tremendous distances. He pointed to several pieces of evidence. The novae in spiral nebulae were about 10 magnitudes fainter than novae in the Milky Way, suggesting distances of millions of light years. Dark lanes visible in some edge-on spirals resembled the dust lanes in our own galaxy, suggesting similar structures. And the spirals showed systematic redshifts. Their light stretched toward longer wavelengths, suggesting they were receding from us at high speeds. The debate itself was inconclusive. Both men presented their evidence. Neither convinced the other, and the audience went home uncertain. History would prove both men partially right and partially wrong. Shapley was correct that the Milky Way was far larger than previous estimates had suggested, but he was wrong to think it comprised the entire universe. Curtis was correct that spiral nebulae were external galaxies, but he clung to older, smaller estimates of the Milky Way's size that Shapley's work had already overturned. The definitive answer came 3 years later from a man who had not participated in the Great Debate at all. Edwin Hubble was an ambitious young astronomer who had recently joined the staff at Mount Wilson Observatory. He had access to the 100-inch Hooker telescope, the largest in the world at the time, and he was using it to photograph spiral nebulae in unprecedented detail. In October of 1923, Hubble was examining photographic plates of the Andromeda Nebula, the largest spiral visible from the northern hemisphere. Andromeda had been observed for over 1,000 years. Persian astronomers had catalogued it in the 10th century. It appeared as a faint, fuzzy oval, about 3 degrees across, visible to the naked eye from dark locations. Through a telescope, it resolved into a maelstrom of light, clearly structured, obviously significant, but of completely unknown nature. Hubble was looking for novae, stellar explosions that occasionally flared in the nebula. Among the countless faint stars in his photograph, he identified what he thought was one. He marked it on the plate with the letters N for nova. But when he compared plates taken on different nights, he realized something strange. The star was not fading away as a nova should. It was varying in brightness, but regularly, rhythmically, brightening and dimming in a repeating pattern. He crossed out the N on his plate and wrote VR instead, variable. And then, with growing excitement, he wrote Cepheid. The implications were immediately clear to him. A cepheid meant a distance measurement. He could apply Henrietta Leavitt's period luminosity relationship and determine how far away the Andromeda Nebula actually was. Hubble measured the period of the variable star, about 31 days. He calculated its true luminosity from Leavitt's relationship. He compared that to its apparent brightness, and he computed the distance, approximately 900,000 light years. The modern value, refined by decades of subsequent observations, is about 2.5 million light years. Hubble's estimate was too small by a factor of nearly 3, partly because his Cepheid calibration was imperfect, and partly because he was unaware that there are actually 2 different types of Cepheid variables with different period luminosity relationships. But even his underestimate was transformative. 900,000 light years was far, far beyond any conceivable boundary of the Milky Way. Even Shapley's inflated estimate of the galaxy's size topped out at about 300,000 light years. Andromeda was 3 times farther than the entire diameter of the Milky Way. It could not possibly be a gas cloud within our galaxy. It had to be an entirely separate system, an island universe in its own right. Hubble found more Cepheids in Andromeda over the following months, Each measurement confirmed the first. He found Cepheids in other spiral nebulae too. Each time, the distances came out in the hundreds of thousands or millions of light years. The spiral nebulae were external galaxies comparable to our own, scattered throughout a universe vastly larger than anyone had imagined. Hubble announced his results at a meeting of the American Astronomical Society in January of 1925. The announcement was met with astonishment and, in some quarters, disbelief. Shapley, in particular, struggled to accept that his enormous Milky Way was not the entire cosmos, but merely one galaxy among countless millions. When Shapley received Hubble's letter detailing the Cepheid discovery, he showed it to a colleague and reportedly said, "Here is the letter that destroyed my universe." The universe had just gotten much, much bigger, and our place in it had gotten much, much smaller. We were not at the center of a galaxy that comprised everything. We were on the outskirts of one ordinary galaxy among billions, in a universe whose true extent was only beginning to be glimpsed. One final piece of the puzzle remained. If Shapley was wrong about the spiral nebulae, was he also wrong about the size of the Milky Way? His measurements gave a galaxy roughly 300,000 light years across, far larger than anyone had previously imagined. But his numbers depended on the assumption that Cepheid variables in globular clusters behave the same way as Cepheids elsewhere, and they depended on ignoring a phenomenon that no one had yet properly accounted for. The answer came in 1930 from Robert Trumpler, an astronomer at Lick Observatory. Trumpler was studying open star clusters, the loose collections of young stars scattered throughout the galactic disk. Unlike globular clusters, which are ancient and orbit in a halo around the galaxy, open clusters are young and embedded within the disk itself. The Pleiades and the Hyades, visible to the naked eye, are nearby examples. Trumpler measured distances to these clusters using two independent methods. First, he estimated distances based on the cluster's angular sizes. A cluster that appears smaller in the sky is presumably farther away, just as a distant car looks smaller than a nearby one. If you know how big clusters typically are in absolute terms, you can use their apparent size to gauge distance. Second, he estimated distances based on the brightness of the cluster's stars. Stars that appear dimmer are presumably farther away. If you know how bright the stars in a cluster truly are, you can use their apparent brightness to gauge distance. If both methods were correct, they should give the same answer. They did not. The brightness-based distances were systematically larger than the size-based distances. Stars appeared fainter than their distances would suggest, and the effect got worse for more distant clusters. There was only one explanation. Something was dimming the light from distant clusters, making them appear farther away than they actually were. That something was interstellar dust. Trumpler had finally identified and quantified the invisible enemy that had plagued astronomers since Herschel. He measured the effect carefully. Starlight dims by roughly 0.7 to 1 magnitude for every kiloparsec, about 3,000 light years, it travels through the galactic disk. Over short distances, the dimming is negligible. Over thousands of light years, it is substantial. Over tens of thousands of light years, it is overwhelming. This discovery forced a fundamental revision of Shapley's model. If interstellar dust was dimming the Cepheids, he used to measure globular cluster distances. Then those clusters were closer than he had calculated. The galaxy was smaller than he had claimed. With Trumpler's correction applied, and with further refinements to the K-fied calibration over subsequent decades, astronomers converged on what remains the modern picture of the Milky Way, a disk roughly 100,000 light-years across and 1,000 to 2,000 light-years thick near the Sun, a central bulge about 10,000 light-years in diameter, spiral arms winding outward from a central bar, and the Sun orbiting in a minor arm called the Orion Spur, about 26,000 light-years from the galactic center. This picture has been refined over the decades, but not fundamentally changed. What has changed dramatically is the precision of our measurements. And for that, we can thank a spacecraft called Gaia. The Gaia mission, launched by the European Space Agency in December of 2013, represents the most ambitious effort to map our galaxy ever attempted. Its instrument is conceptually simple, but technologically extraordinary. Gaia measures the positions of stars over and over again as it orbits the Sun. As Earth and Gaia move through space, nearby stars appear to shift slightly against the background of more distant stars, an effect called parallax. By measuring this shift with extreme precision over multiple years, Gaia can calculate distances directly without relying on assumptions about stellar brightness or Cepheid calibrations or any other indirect method. Gaia's precision is almost incomprehensible. It can measure angular positions to about 20 microarcseconds. Let me explain what that means. An arcsecond is 1/3600th of a degree, roughly the apparent size of a dime seen from 4 kilometers away. A microarcsecond is 1/1,000,000th of that. Gaia can measure angles equivalent to the diameter of a human hair seen from 1,000 kilometers, or the width of a coin on the moon as viewed from Earth. With this extraordinary precision, Gaia has measured distances to stars throughout the Milky Way, not just the nearby ones that previous parallax surveys could reach. The third major data release, published in June of 2022, contained measurements of nearly 2 billion stars, not just positions and distances, but also motions through space, temperatures, chemical compositions. It is the most detailed census of the Milky Way ever compiled, and astronomers will be mining it for discoveries for decades to come. Gaia has revealed the wreckage of ancient galactic collisions, a structure called Gaia Enceladus, also known as the Gaia sausage because of the distinctive elongated shape of its star's orbits, represents the debris of a dwarf galaxy that collided with the Milky Way 8 to 11 billion years ago. The collision was catastrophic. The smaller galaxy was completely destroyed, its stars stripped away and absorbed into the Milky Way's halo. But the chemical fingerprints and orbital characteristics of those stars remain distinct, ghosts of a galaxy that no longer exists as an independent entity. Gaia has also revealed streams of stars stretched across the sky, the remnants of globular clusters and smaller galaxies that ventured too close and were torn apart by the Milky Way's gravity. It has mapped the warping of the outer galactic disk, a subtle bending above and below the midplane that may result from ongoing interactions with satellite galaxies. It has refined our understanding of the spiral arms and the central bar. And in September of 2023, an analysis of Gaia data produced a finding that, if confirmed, could reshape our understanding of the galaxy's mass. For decades, astronomers had observed that stars in the outer regions of the Milky Way orbit faster than expected. In our solar system, planets farther from the Sun orbit more slowly because the Sun's gravitational pull weakens with distance. But in the Milky Way, stars at the outer edge orbit at nearly the same speed as stars much closer to the center. This flat rotation curve, as it is called, implies that the galaxy contains far more mass than the visible stars can account for. That invisible mass is what we call dark matter. But the 2023 Gaia analysis found something different. When astronomers traced stellar motions in the far outer galaxy, beyond about 50,000 light-years from the center, they found that the rotation curve finally begins to decline. Stars out there are moving slower than the flat rotation curve would predict. This Keplerian decline, named after the laws Johannes Kepler derived for planetary motion, suggests that the dark matter halo may be less massive than previously thought. If this finding holds up, the total mass of the Milky Way could be revised dramatically downward. Previous estimates put the galaxy's mass at roughly 1.5 trillion times the mass of the Sun, with dark matter accounting for about 90% of that total. The new analysis suggests the true mass might be closer to 200 billion solar masses, 4 to 5 times lower. This finding remains controversial. Other research groups have not replicated it. The measurements at such extreme distances are difficult and prone to systematic errors. But it illustrates an important point. Even after 2 centuries of study, we are still refining our understanding of our own galaxy. The Milky Way is vast and complex, and there is much we do not yet know. Now that we understand how big the galaxy is and how hard-won that knowledge was, let me walk you through what it would actually mean to escape it. We need to start by establishing our position precisely. The Sun sits in the Orion Arm, also called the local arm or the Orion Spur, a relatively minor spiral feature that connects the larger Sagittarius and Perseus arms. We are not in one of the galaxy's main spiral arms, but rather in a spur between them. Our distance from the galactic center is approximately 26,000 light-years, with an uncertainty of about 1,000 light-years. This places us roughly halfway between the center and the outer edge of the visible stellar disk. We are in the galactic suburbs, far from the crowded downtown core, but not out in the distant exurbs either. We are also very close to the galactic midplane, the imaginary flat surface that runs through the center of the disk. The Sun currently sits about 50 to 100 light-years above this midplane, essentially dead center in the vertical direction. But this position is not permanent. The Sun oscillates up and down through the disk over a period of about 66 million years, reaching heights of up to 250 light-years above and below the plane. We happen to be near the midpoint of this oscillation right now. Our location has been described as the galactic habitable zone, a region with conditions favorable for life. We are far enough from the violent galactic core to avoid frequent supernova explosions and close gravitational encounters with other stars. We are close enough to have the heavier chemical elements produced by previous generations of stars that are necessary for rocky planets and complex chemistry. Whether the galactic habitable zone is a meaningful concept or merely a coincidence remains debated, but our location is certainly a pleasant one by cosmic standards. Now, let me walk you through each of the 4 escape routes in detail. Escape Route 1, perpendicular to the disk. This is the fast way out. Head straight up from the plane of the galaxy, perpendicular to the midplane, and you minimize the distance you need to travel through the stellar disk. The Milky Way's disk has 2 components. The thin disk, which contains about 90% of the disk's stars, extends roughly 1,000 light-years above and below the midplane. This is where you find the young stars, the gas and dust, the regions of active star formation. The Sun and most of the familiar stars in our night sky belong to the thin disk. The thick disk is a separate population of older stars extending about 2,000 to 3,000 light-years above and below the midplane. These stars are typically 10 billion years old or more, with lower abundances of heavy elements. They were born in an earlier era, before the disk had fully settled into its current thin configuration. At light speed, you would pass through the thin disk in about 500 years. The star density would drop steadily as you climbed, from the hundreds of stars per cubic parsec in the midplane to just a handful per cubic parsec at the disk's edge. By 1,000 light-years, you would be leaving the thin disk behind. Looking back, you would see the galactic plane stretching out below you, a luminous band of light containing hundreds of billions of stars. The view would be spectacular, the entire structure of the Milky Way laid out like a map. By 2,000 to 3,000 light-years, you would be exiting the thick disk as well. The stars around you would become increasingly sparse, predominantly ancient red dwarfs and the occasional globular cluster. What would you see along the way? The first few hundred light-years would look much like our current night sky, stars in every direction with no obvious structure. But as you climbed higher, the disk would begin to reveal itself. The Milky Way would transform from an immersive environment surrounding you on all sides into a visible object that you could see from outside. At 1,000 light-years, you could trace the spiral arms winding outward from the central bulge. You could see the dark lanes of dust that bisect the disk when viewed edge-on. You could appreciate the central bar connecting the bulge to the spiral structure. Our galaxy would become comprehensible as a coherent structure for the first time. Above you, mostly emptiness. The stellar halo is extremely sparse, with perhaps 1 star per 1,000 cubic light-years on average. You might pass the occasional globular cluster, ancient swarms of hundreds of thousands of stars orbiting the galaxy in tilted elliptical paths. But mostly, you would be traveling through void. The journey through the thin disk would take about 500 years. Through the thick disk, perhaps 2,000 to 3,000 years. But you would not have truly escaped the Milky Way. Not yet. The stellar halo extends far beyond the disk. Globular clusters orbit out to about 130,000 light-years from the galactic center. Individual halo stars have been detected at even greater distances. The stellar halo gradually fades, but it does not have a sharp edge. And beyond the stellar halo lies the dark matter halo. This enormous envelope of invisible mass extends to roughly 950,000 light-years from the galactic center, based on recent measurements. It contains no stars, no planets, no gas or dust, nothing visible at all. But it contains most of the galaxy's mass, and its gravitational pull defines the true boundary of the Milky Way. At light speed, crossing the dark matter halo would take roughly 1,000,000 years. You would spend a few thousand years escaping the stellar disk, then the better part of 1,000,000 years crossing essentially empty space, with nothing to mark your progress except the gradually diminishing gravitational pull of the galaxy behind you. When would you finally be free? When the Milky Way's gravity no longer had any significant influence on your motion? When you were equally subject to the pulls of other galaxies in the local group? That boundary lies somewhere around 1,000,000 light-years from the galactic center, roughly 1/3 of the way to the Andromeda galaxy. At light speed, even taking the shortest route, truly escaping the Milky Way would take nearly 1,000,000 years. This is perhaps the most counterintuitive aspect of our galaxy's structure. The visible part, the disk of stars we can photograph and measure, is only a small fraction of the total extent. Most of the Milky Way is invisible. Most of it is empty. Most of it is dark matter, interacting with ordinary matter only through the inescapable pull of gravity. If you could somehow watch your ship's progress on a map during this perpendicular escape, you would see yourself racing through the first few thousand light years, the region of visible stars, in what would feel like rapid progress. Then you would enter the halo, and the map would seem to freeze. Year after year, century after century, millennium after millennium, you would crawl across what appeared to be empty space. The galaxy behind you would shrink, eventually becoming just another smudge of light among many. But the gravitational boundary would approach with agonizing slowness. This is the true scale of our galaxy, not the 100,000 light years we usually cite, nearly 2,000,000 light years. If you count the full gravitational extent, we are embedded in something almost incomprehensibly large, and most of it is invisible. Escape Route 2, toward the galactic center. This is the scenic route, 26,000 light years through some of the most spectacular territory in the galaxy, culminating in the most extreme environment imaginable. From Earth, the galactic center lies in the direction of the constellation Sagittarius, visible in the summer sky from the northern hemisphere. But we cannot see it directly. Vast clouds of interstellar dust block our view, absorbing visible light so completely that the center is invisible to optical telescopes. There are roughly 30 magnitudes of extinction between us and the galactic center, meaning the light is dimmed by a factor of about 1,000,000,000,000. If we could somehow remove the dust, the central bulge of the Milky Way would be one of the brightest objects in our sky. Everything we know about the galactic center comes from observations at wavelengths that can penetrate the dust. Infrared light, with wavelengths longer than visible light, passes through more easily. Radio waves ignore the dust entirely. X-rays from orbiting telescopes provide yet another window. By combining observations across the electromagnetic spectrum, we have built up a detailed picture of what lies at the heart of our galaxy. Setting out toward the galactic center at light speed, you would first pass through our immediate neighborhood, the local bubble. This is a region about 1,000 light years across, where the interstellar medium is unusually thin, probably carved out by supernova explosions within the past 10 to 20 million years. The Sun sits near one edge of this bubble. Traveling inward, you would pass through its boundary within 1,000 years. Beyond the local bubble, you would traverse the rest of the Orion Arm. This is a region of moderate star formation, containing the famous Orion Nebula, about 1,300 light-years away, as well as numerous other stellar nurseries and associations of young stars. The Orion Arm is not a major spiral feature like the Sagittarius or Perseus arms, but more of a spur or bridge connecting them. Continuing inward, you would cross the inter-arm region between Orion and Sagittarius. This is a relatively sparse zone, a few thousand light-years across, with less gas and dust and fewer young stars than the arms themselves. Then, around 4,000 to 6,000 light-years from Earth, you would enter the Sagittarius Arm, one of the galaxy's major spiral features. And here, the journey becomes truly spectacular. The Sagittarius Arm is one of the most active regions of star formation in the Milky Way. It contains some of the most famous and beautiful objects in the night sky, spectacles that would be visible from far closer distances than we can currently achieve. The Eagle Nebula lies about 6,000 light-years away in the Sagittarius Arm. It hosts the pillars of creation, those towering columns of gas and dust photographed by the Hubble Space Telescope in 1995, and again by the James Webb Space Telescope in 2022. The pillars are 4 to 5 light-years tall, sculpted by the intense ultraviolet radiation from nearby hot young stars. Within their shadowed interiors, protected from the scouring radiation, new stars are being born even now. The pillars will not last forever. In a few million years, the radiation will have evaporated them entirely, exposing the young stars within. Imagine approaching the Eagle Nebula at light speed. From thousands of light-years away, it would appear as a faint smudge, barely distinguishable from the background glow of the galactic plane. As you drew closer, over centuries, it would resolve into structure. The central star cluster would become visible, dozens of bright blue-white stars pouring out radiation. The surrounding gas would glow in the characteristic pink of ionized hydrogen. At a distance of a few light-years, the pillars themselves would dominate the view. They would appear not as the static photographs we know, but as dynamic structures, their surfaces rippling and changing over timescales of years as radiation pressure sculpted new forms. Light-year tall fingers of gas reaching into space, lit from within by newborn stars, eroding even as they give birth. The Omega Nebula, also called the Swan Nebula, lies about 5,000 light-years away. It is a glowing cloud of ionized hydrogen, about 15 light-years across, one of the most luminous star-forming regions known. At its heart, massive stars, tens of times the Sun's mass, are consuming their fuel at prodigious rates, destined to explode as supernovae within a few million years. The Lagoon Nebula is larger still, stretching 110 by 50 light-years, about 4,000 light-years from Earth. Its central region contains a remarkable structure called the Hourglass Nebula, where the radiation from the central star has carved a double-lobed cavity in the surrounding gas. The lagoon is one of only 2 star-forming regions visible to the naked eye from Earth, appearing as a faint patch of light in the constellation Sagittarius on summer nights. The Trifid Nebula, about 5,000 light-years distant, combines 3 different types of nebulosity in one spectacular object. An emission nebula glows pink with ionized hydrogen. A reflection nebula shines blue with scattered starlight. Dark nebulae, dense clouds of dust that block the light behind them, divide the structure into apparent thirds, giving the object its name. The Trifid is young by cosmic standards, perhaps only 300,000 years old. As you pass through the Sagittarius arm at light speed, these nebulae would drift by over centuries. Each would grow from a distant smudge to a resolved structure to a dominant presence to a receding memory, replaced by the next wonder. Star clusters would appear and disappear. Young associations of blue giants would blaze briefly before falling behind. The journey would be a parade of cosmic spectacles unmatched anywhere else in the galaxy, but the arm would eventually end. This is an elongated structure about 27,000 light-years long, oriented at roughly 27 degrees relative to our line of sight to the galactic center. The bar consists predominantly of old red and orange stars, with little ongoing star formation. It is a more settled, stable region than the spiral arms. The bar channels gas inward toward the galactic center, like water swirling down a drain. This gas feeds the activity in the central regions, providing raw material for bursts of star formation, and possibly for the central black hole itself. Inside the bar, within about 5,000 light-years of the galactic center, lies the central molecular zone. This is a ring of dense molecular gas clouds orbiting the nucleus. Temperatures and pressures here far exceed anything in our neighborhood. Molecular clouds in the central molecular zone are hotter and denser than typical molecular clouds elsewhere in the galaxy. Massive stars form here, live fast, and die young. The innermost region of the galaxy is utterly unlike anywhere else. Within the central parsec, about 3.2 light-years, roughly 10 million stars are packed into a volume that in our neighborhood would contain perhaps a dozen. The stellar density is about 1 million times higher than around the Sun. The stars here have bizarre orbits. Instead of the nearly circular paths that stars follow in the disk, stars near the galactic center trace highly elliptical orbits around the central mass. Some complete their orbits in just a few years. The star S2, one of the best studied, orbits the galactic center every 16 years, reaching speeds of about 8,000 kilometers per second at closest approach. At the very center sits Sagittarius A star, the supermassive black hole. Its mass is about 4.1 million times the mass of the Sun, all compressed into a region with a Schwarzschild radius of about 12 million kilometers. If you placed it where the Sun is, its event horizon would fit comfortably inside Mercury's orbit. We know this object is a black hole because we have watched stars orbit it. The motions of S2 and other stars near the galactic center trace out Keplerian ellipses around an invisible central mass, exactly as planets orbit the Sun. No object other than a black hole could pack 4 million solar masses into a region small enough to permit such tight orbits. The Event Horizon Telescope collaboration imaged Sagittarius A star directly in 2022, or rather, imaged the glowing gas orbiting just outside its event horizon. The result shows a bright ring surrounding a dark central shadow, the silhouette of the black hole against the light it cannot escape. The image matches the predictions of Einstein's general relativity almost exactly. Sagittarius A star is relatively quiet now, accreting matter slowly, flaring occasionally when a gas cloud or unlucky star ventures too close. But enormous structures suggest more violent episodes in the past. The Fermi bubbles, discovered in 2010, are vast lobes of energetic plasma extending 25,000 light-years above and below the galactic center. They may be the remnants of a massive outburst millions of years ago, when the black hole consumed a large amount of matter and erupted with energy. The journey to the galactic center would take 26,000 years at light speed. You would travel from the quiet suburbs of the Orion Arm through the spectacular star-forming regions of the Sagittarius Arm into the dense stellar city of the Central Bulge, and finally into the extreme environment surrounding a supermassive black hole. It would be a journey from the familiar to the utterly alien. Escape Route 3, toward the outer rim. In the opposite direction lies the long road outward, 25 to 30,000 light-years to the edge of the visible disk, through increasingly sparse stellar populations, into the dim outer reaches where the galaxy fades into the intergalactic void. Heading outward from Earth, you would first cross the remainder of the Orion Arm, a journey of perhaps 2,000 light-years. Then you would enter the inter-arm region between Orion and Perseus, a relatively empty zone several thousand light-years across. The Perseus Arm is one of the galaxy's two major spiral arms, curving around the disk in a grand sweep tens of thousands of light-years long. It is rich in young stars and star-forming regions, though somewhat less active than the Sagittarius Arm, nearer the galactic center. Crossing Perseus would take several thousand years at light speed. Beyond Perseus lies the outer arm, sometimes called the Cygnus Arm, the last major spiral structure before the disk begins to fade. Stars here are older on average, with fewer massive blue giants and more long-lived red dwarfs. The chemical composition changes too. Heavy elements like iron, oxygen, and silicon become less abundant as you move outward, because fewer generations of supernovae have enriched the interstellar medium. Past the outer arm, the disk gradually thins. Stellar density drops exponentially with distance from the galactic center. By 40,000 light-years out, about 14,000 light-years from Earth, you would be in the extreme outer disk. Stars become sparse, often separated by tens of light-years. The spiral structure fades into a smooth, thin population of isolated stars. At 50,000 light-years from the center, you would reach what was traditionally considered the edge of the stellar disk. But recent surveys have found stars even farther out, sparse populations extending to perhaps 80,000 or even 100,000 light-years. These are the true galactic fringe dwellers, ancient stars in isolation so extreme that their nearest neighbors might be hundreds of light-years away. The outer disk also warps. Instead of lying perfectly flat, it bends above and below the midplane at large distances from the center. This warp may be caused by gravitational interactions with satellite galaxies, particularly the Magellanic Clouds, or by the infall of gas from intergalactic space. From your vantage point, approaching the outer edge, you would see this warp clearly, the disk bending like a hat brim caught by wind. The warp is substantial. At the outer edges, the disk deviates by several thousand light-years from the idealized flat plane. If you were traveling outward along the midplane, you would eventually find yourself above or below the disk as it curved away from you. The Milky Way is not a perfect flat coin. It is more like a warped vinyl record, twisted by the gravitational tugs of smaller galaxies that have passed nearby over billions of years. The stars in the outer disk are old. Most formed more than 8 billion years ago, before the disk had fully developed its current structure. They orbit on paths that are often more elliptical than the nearly circular orbits of stars in the inner disk. Some may be remnants of smaller galaxies that were absorbed long ago, their stars now indistinguishable from native Milky Way stars except by their chemical compositions and orbital properties. As you traveled outward, the density of stars would drop exponentially. Near the Sun, there are roughly 10 million stars within 1,000 light years in any direction. Near the edge of the disk, that same volume might contain only a few thousand. Beyond about 50,000 light years from the center, you would be lucky to find a single star within 100 light years of your position. The view looking back would be breathtaking. The entire Milky Way spread out behind you, a vast spiral of light containing hundreds of billions of stars. You could see the complete pattern of the spiral arms, the bright central bulge, the dark dust lanes that thread through the disk. You would see our galaxy as a coherent structure for the first time, not from the inside, but from the outside. The Andromeda galaxy would be visible too, a smaller but still substantial spiral about 2.5 million light years away. The other members of the local group would appear as faint smudges, the Triangulum galaxy and the Magellanic Clouds and the dozens of dwarf galaxies that orbit in our gravitational neighborhood. The journey to the outer rim would take 25 to 30,000 years at light speed. But as with the perpendicular escape, reaching the visible edge of the disk would not mean you had truly escaped the galaxy. The stellar halo extends farther, the dark matter halo much farther still. Escape Route 4. To the true edge. The Milky Way does not end where its stars end. It ends where its gravitational influence fades into the gravitational background of the local group and the wider universe. Defining this true edge is not straightforward. Gravity has infinite range, technically speaking, but there comes a point where the Milky Way's pull becomes comparable to or weaker than the pulls of neighboring galaxies. Beyond that point, an object is no longer meaningfully bound to our galaxy. Recent studies place this boundary at roughly 950,000 light years from the galactic center. At this distance, the dark matter halo finally peters out, its density dropping to match the sparse intergalactic medium. Objects here are as likely to be influenced by Andromeda or other local group members as by the Milky Way itself. The journey to the true edge would take nearly 1 million years at light speed. After a few thousand years escaping the stellar disk, you would enter a vast emptiness. The occasional globular cluster or halo star would punctuate the void, but mostly you would be traveling through nothing at all. No gas, no dust, no visible landmarks, just the dark matter that you cannot see, whose presence you can only infer from its gravitational effects. And here is a remarkable fact. The true edge of the Milky Way's halo nearly touches the true edge of Andromeda's halo. The two galaxies are separated by about 2.5 million light years at their closest points, but their dark matter halos each extend roughly 1 million light years. There is essentially no truly empty space between them. The two largest galaxies in the local group are already in contact, their outer envelopes overlapping, even though their visible disks remain distinct. This is not an abstract observation. In about 4 to 5 billion years, the Milky Way and Andromeda will collide. the approach has already begun. Andromeda is moving toward us at about 110 kilometers per second, one of the few galaxies in the universe that shows a blue shift rather than a red shift. Every second, the gap between our galaxies shrinks by 110 kilometers. When the collision finally occurs, it will not be the violent crash that the word suggests. Galaxies are mostly empty space. Even in the densest regions, stars are separated by trillions of kilometers. When Andromeda's disk passes through ours, the individual stars will almost certainly not collide. They will simply pass by each other, gravitationally deflected, but physically untouched. But the gravitational effects will be profound. The spiral structures of both galaxies will be disrupted and eventually destroyed. Stars will be flung onto chaotic new orbits. Tidal tails of material will stream outward, some stars escaping into intergalactic space. Over hundreds of millions of years, the two galaxies will orbit around each other, passing through again and again, losing energy to dynamical friction until they finally merge into a single larger galaxy. Computer simulations of this process produce striking images. The familiar spiral forms give way to chaotic tangles of stars. Tidal bridges connect the merging cores. Eventually, a new elliptical galaxy emerges from the wreckage, a bloated sphere of stars with no spiral structure and little ongoing star formation. Astronomers have nicknamed this future merger product Milkomeda, or sometimes Milkdromeda. From Earth's perspective, if Earth still exists in 5 billion years, the night sky will be transformed. Andromeda, currently a faint smudge visible to the naked eye, will grow larger and larger over hundreds of millions of years. Eventually, it will dominate the night sky, a vast band of light far brighter than the current Milky Way. Then the two bands will merge, interweave, and finally combine into a new configuration that no human eyes have ever seen. The Sun will still exist during the early phases of this merger, though it will have swelled into a red giant and likely rendered Earth uninhabitable. Whether any descendants of humanity will witness the collision is unknowable, but the collision itself is as certain as anything in astronomy. The gravitational calculation is straightforward. The approach is already underway. The only question is the details of how the merger will unfold. So to truly escape the Milky Way, you would need to escape not just our current galaxy, but the merged product that will exist in 5 billion years. And that merged product will itself be part of the local group, gravitationally bound to dozens of other galaxies in a structure about 10 million light years across. I have been discussing light speed travel as though it were merely difficult, a matter of sufficient technology and time. But the truth is stranger and more limiting than that. According to Einstein's special theory of relativity, nothing with mass can travel at the speed of light. This is not a technological limitation that future civilizations might overcome. It is a fundamental property of the universe, woven into the geometry of space-time itself. The mathematics are unforgiving. As an object accelerates, its effective inertia increases. At low speeds, this effect is negligible. But as you approach the speed of light, the energy required for each additional increment of velocity grows without bound. To accelerate a spacecraft to 90% of light speed requires enormous energy. To reach 99% requires about 7 times more. To reach 99.9% requires another factor of 7. The progression continues without end. To accelerate anything with mass to exactly the speed of light would require infinite energy. Since infinite energy does not exist, light speed is impossible to achieve. But special relativity contains another prediction that is, in some ways, even more strange. Time dilation. As an object moves faster relative to a stationary observer, time passes more slowly for the moving object. This is not a perceptual trick or a mechanical failure of clocks. Time itself actually passes more slowly. Every physical process, every chemical reaction, every beat of the heart, every thought in the brain, all slow down for the moving observer. The mathematical relationship is given by the Lorentz factor, usually represented by the Greek letter gamma. At rest, gamma equals 1, and time passes normally. At 50% of light speed, gamma is about 1.15. At 90%, gamma is about 2.3. At 99%, gamma is about 7.1. At 99.9%, gamma is about 22.4. At 99.99%, gamma is about 70.7. The implications for interstellar travel are profound and strange. Consider a journey to the galactic center, 26,000 light-years away. From the perspective of someone on Earth, this journey cannot possibly take less than 26,000 years. Light itself takes that long, and nothing travels faster than light. But from the perspective of a traveler moving at high speed, the journey can be much shorter. At 99% of light speed, the traveler would age about 3,700 years during the journey. At 99.99%, only about 370 years. At 99.999%, about 116 years. Let me work through these numbers more carefully, because they illustrate something profound about the nature of space and time. At 99% of light speed, the Lorentz factor gamma equals 7.1. This means time passes 7 times slower for the traveler than for an observer on Earth. The journey still takes 26,000 years in Earth's reference frame, but the traveler experiences only about 3,700 years of subjective time. They arrive having aged 3,700 years, while Earth has aged 26,000. At 99.9% of light speed, gamma equals 22.4. The traveler experiences about 1,160 years. At 99.99%, gamma equals 70.7. The traveler experiences about 370 years. At 99.999%, gamma equals 224. The traveler experiences about 116 years. You can see the pattern. Each additional 9 in the velocity brings roughly another factor of 3 in time dilation. To reduce the subjective journey to a single human lifetime, you need to travel at roughly 99.9995% of light speed, where gamma exceeds 400. But the energy requirements scale even faster. The kinetic energy of a moving object at relativistic speeds is given by gamma minus 1 times the rest mass energy at 99.9995% of light speed. Gamma is about 450. This means the kinetic energy of your spacecraft would be about 450 times its rest mass energy. If your ship had a rest mass of 1,000 tons, you would need to supply energy equivalent to 450,000 tons of matter converted entirely to energy via E equals mc squared. For comparison, the entire energy output of the Sun over 1 second is equivalent to about 4 million tons of matter. Your ship would need roughly 1/10 of a second of the Sun's total output, focused and converted with perfect efficiency into directed motion. And that is just to accelerate. You would need the same again to decelerate at the other end. The engineering challenges are beyond anything we can currently imagine. But the physics does not forbid it. The universe permits relativistic travel, at least in principle. It is merely staggeringly difficult. How is such time dilation possible? From the traveler's perspective, distances contract in the direction of motion. At 99.99% of light speed, the 26,000 light-years to the galactic center would appear to be only about 370 light-years. The traveler does not experience time passing slowly. From their point of view, time passes normally, but the universe shrinks. Both descriptions are mathematically equivalent and physically correct. The stationary observer sees time passing slowly for the traveler sees distances contracting. Both are accurate descriptions of the same physical reality, viewed from different reference frames. This creates a profound asymmetry. In principle, a human being could travel to the galactic center within a single biological lifetime if you could somehow accelerate close enough to light speed. A spacecraft maintaining constant acceleration at 1g, equivalent to Earth's surface gravity, would reach near light speed in about 1 year of ship time. Under constant acceleration to the midpoint and then deceleration for the second half, a traveler could reach the galactic center in about 20 years of subjective experience. But those 20 years would cost 26,000 years back on Earth. Everyone the traveler knew would be dead. Every civilization they remembered would be ancient history. Every language they spoke would have evolved beyond recognition or gone extinct. They would arrive at the galactic center not as explorers who left recently, but as time travelers displaced by millennia. And if they chose to return, the cost would double. Another 20 years of ship time, another 26,000 years on Earth. They would come back to a world 52,000 years older than the one they left. This is longer than the entirety of human civilization, longer than modern humans have existed as a species. Relativistic travel is possible in principle, but it is a one-way journey through time. You can visit the future, but you cannot return to the present. Let me put the galactic distances in perspective through comparison with more familiar cosmic journeys. Start with the solar system. At light speed, you would reach the Moon in 1.3 seconds. The planet Mars, at its closest approach, in about 3 minutes. Jupiter in 35 to 50 minutes, depending on orbital positions. Neptune, the outermost major planet, in about 4 hours. The edge of the solar system is harder to define. The heliopause, where the solar wind meets the interstellar medium, lies about 120 astronomical units from the Sun. Light covers this distance in about 17 hours. Voyager 1 crossed the heliopause in 2012 after 35 years of travel. But the solar system extends much farther. The Oort cloud, that vast spherical shell of icy bodies that occasionally sends comets toward the inner planets, may extend from about 2,000 to perhaps 100,000 astronomical units. At light speed, reaching the outer edge takes roughly a year and a half. So at light speed, escaping the solar system entirely takes about 18 months. Escaping the thin disk of the Milky Way takes about 1,000 years. The ratio is roughly 500 to 1. The galaxy is 500 times harder to escape than the solar system. Now consider stars. The nearest, Proxima Centauri, lies about 4.24 light-years away. At light speed, you arrive in a little over 4 years. But at the actual speeds achieved by human spacecraft, the journey is far longer. Voyager 1, traveling at about 17 kilometers per second, would need roughly 73,000 years to cover the same distance. The Andromeda galaxy, our nearest large neighbor, lies about 2.5 million light-years away. At light speed, the journey takes 2.5 million years. This is roughly 100 times longer than crossing the Milky Way's disk. The gulfs between galaxies dwarf the distances within them. The local group spans about 10 million light-years. The Virgo supercluster extends roughly 100 million light-years. The observable universe has a diameter of about 93 billion light-years. That last number seems impossible. The universe is only about 13.8 billion years old. How can we see 93 billion light-years in any direction? The answer is cosmic expansion. Space itself is expanding, carrying distant galaxies away from us. Light that left a distant galaxy billions of years ago has been traveling toward us while the space between us stretched. The galaxy that emitted that light has been carried even farther away by the expansion. We see that galaxy as it was when younger and closer, but its present-day position is much more remote. This expansion creates an absolute barrier. Galaxies beyond a certain distance are receding from us faster than the speed of light. Not because they are moving through space faster than light, which is impossible, but because the space between us is expanding that fast. Light we emit today will never reach those galaxies. Light they emit today will never reach us. They are forever beyond our cosmic horizon. We are prisoners of our own cosmic neighborhood, not just the Milky Way, not even the local group, but a larger volume of space from which nothing can ever escape, no matter how fast it travels. Let me offer some scale comparisons to make these numbers more tangible. Imagine the Sun as a grain of sand, about 0.5 millimeter in diameter. At this scale, the Earth would be a microscopic speck orbiting about 8 centimeters away. Neptune would orbit at about 3 meters. The outer edge of the Oort cloud would lie roughly 2 kilometers distant. The nearest star, Proxima Centauri, would be another grain of sand about 6.5 kilometers away. The galactic center would be 40,000 kilometers distant. That is roughly the circumference of the actual Earth. If the Sun were a grain of sand in Singapore, the galactic center would be a grain of sand on the opposite side of the planet. At this scale, the entire visible disk of the Milky Way would span about 150,000 kilometers, somewhat more than the distance from the Earth to the Moon. The dark matter halo would extend about 1.4 million kilometers, roughly 10 times the diameter of the actual Sun. Here is another comparison. If you could drive to the stars at highway speed, say 100 kilometers per hour, reaching the Moon would take about 4 months. Reaching the Sun would take about 170 years. Reaching Proxima Centauri would take 46 million years. Reaching the galactic center would take about 280 billion years. That last number is 20 times the current age of the universe. You would need to drive for 20 cosmic lifetimes to reach the center of our own galaxy. Even at the speed of the fastest spacecraft ever built, the journey is measured in geological time. The Parker Solar Probe reaches about 170 kilometers per second during its closest passes around the Sun. At that speed, reaching the galactic center would take 46 million years, roughly the time since the dinosaurs went extinct. One more aspect of galactic escape deserves mention: escape velocity. To permanently leave the Milky Way, you need to exceed the local gravitational escape velocity, the minimum speed at which you will coast away forever rather than falling back. Near the Sun's position, this escape velocity is about 550 kilometers per second. The Sun orbits the galactic center at about 230 kilometers per second, roughly 40% of escape velocity. We are gravitationally bound, destined to circle the galactic center indefinitely. At our current orbital speed, one lap takes about 220 to 250 million years. The Sun has completed roughly 18 to 20 orbits since it formed 4.5 billion years ago. But some stars have been accelerated to escape velocity. These hypervelocity stars hurtle through the galaxy at over 1,000 kilometers per second, fast enough to leave entirely. About 20 or 30 hypervelocity stars have been confirmed. The current record holder is S5HVS1, discovered in 2019. It travels at about 1,755 kilometers per second, roughly 0.6% of light speed. At this speed, it will escape the Milky Way within a few 100 million years. The origin of hypervelocity stars typically involves the supermassive black hole. When a binary star system passes too close to Sagittarius A star, the intense gravity can disrupt the pair. One star gets captured into orbit around the black hole. The other gets flung outward at tremendous speed like a stone from a gravitational slingshot. S5HVS1 shows the chemical fingerprints of a star born near the galactic center, and its trajectory traces back to that region. It is almost certainly a survivor of a close encounter with a supermassive black hole, ejected with more than enough velocity to eventually escape the galaxy. Let me close with a thought experiment that brings all of this together. Imagine you could build a spacecraft capable of accelerating at a constant 1 GG indefinitely. This would require an energy source far beyond current technology, perhaps matter-antimatter annihilation at near-perfect efficiency. But it does not violate any known laws of physics. Under constant 1g acceleration, you would feel comfortable Earth-like gravity throughout the journey. You would reach near light speed in about 1 year of ship time. From then on, time dilation would increasingly compress your subjective experience relative to the universe outside. If you accelerated at 1g toward the galactic center until the midpoint, then decelerated at 1g for the second half, you would arrive in about 20 years of ship time. 20 years of meals and sleep and watching the stars outside shift through bizarre relativistic distortions. 20 years of maintaining equipment, monitoring systems, and wondering what awaits at the journey's end. But during those 20 years, 26,000 years would pass on Earth. When you arrived at the galactic center, you would step out of your spacecraft into a universe profoundly altered. The constellations would be unrecognizable. Stars that were bright in our sky would have dimmed, moved, or died. New stars would have formed, lived, and exploded. 26,000 years of stellar evolution would have reshaped the cosmic landscape. And Earth, 26,000 years is longer than the entire history of human civilization. The oldest cave paintings are about 40,000 years old. The oldest cities are about 10,000 years old. Writing was invented about 5,000 years ago. In 26,000 years, everything we have ever built will be archaeological debris, if it exists at all. Would humans still exist? It is impossible to say. Evolution works on timescales of millions of years, so our descendants would likely still be recognizably human. But their cultures, languages, and technologies would be as alien to us as we would be to the cave painters of Lascaux. We would share DNA, but little else. You could turn around and return. Another 20 years of ship time. Another 26,000 years on Earth. You would arrive home 52,000 years after you left. Everything you knew would be not just ancient, but fossilized in geological strata. The very coastlines would have shifted. Climate would have cycled through ice ages and warm periods. The positions of the stars would have noticeably changed. The poet T.S. Eliot wrote that time present and time past are both perhaps present in time future, and time future contained in time past. But relativistic travel breaks this poetic unity. At near light speed, time present splits into fragments. Your present and Earth's present become irreconcilably separated. You cannot share a moment with anyone you left behind, because your moments and their moments no longer align. This is the true cost of interstellar travel. The universe is not too big to explore, exactly. It is too big to explore and return. Every journey to distant stars is a journey forward through time, from which there is no coming back. You can visit the future, but you can never visit the present you left behind. Science fiction often imagines faster than light travel as a solution to this problem. Warp drives, wormholes, hyperspace. But the physics we understand does not permit these escapes. The speed of light is not merely a technological barrier, but a fundamental property of space-time geometry. Exceeding it would be like traveling north from the North Pole. The concept does not pass. Some physicists have speculated about exotic possibilities. The Alcubierre drive, for instance, describes a theoretical bubble of space-time that contracts in front and expands behind, carrying a spacecraft faster than light without locally violating relativity. But such a drive would require negative energy densities, something that may not exist outside of quantum fluctuations. And even if it could be built, it might create causality paradoxes that the universe somehow prevents. For now, and perhaps forever, we are stuck with subliminal travel. And that means we are stuck with the time dilation that comes with it. The Milky Way contains somewhere between 100 billion and 400 billion stars. The uncertainty is embarrassingly large for such a fundamental number, but it reflects the difficulty of counting faint red dwarf stars that dominate by number but contribute little light. The true count is probably closer to 200 billion. Those stars are accompanied by planets. The Kepler Space Telescope, which operated from 2009 to 2018, revealed that planets are common. Nearly every star hosts at least one planet. Many host several. rocky planets in the habitable zones of their stars, where liquid water could potentially exist, number in the billions. In one sense, we have already explored many of these worlds. We have measured their sizes, estimated their masses, determined their orbital periods, even detected the compositions of some of their atmospheres. The James Webb Space Telescope can analyze starlight that has passed through exoplanet atmospheres, identifying molecular signatures of water vapor, carbon dioxide, and other compounds. But we have not visited them. We have not walked on their surfaces or sampled their geology or searched for life in their oceans. We have looked, but we have not traveled. And given the distances involved, we may never travel. Not to most of them, not to the vast majority of them. The galaxy is simply too large. This is a strange situation for a species that has, until now, been able to eventually reach any place it could see. Humans spread from Africa across every continent except Antarctica, and eventually we reached Antarctica too. We crossed the Pacific Ocean in fragile canoes, navigated the Atlantic in wooden ships, flew across the sky in aluminum tubes. Every horizon invited exploration, and eventually exploration reached it. But the galactic horizon is different. We can see it clearly. We can study it in detail. We can catalogue its contents with extraordinary precision, but we cannot reach it. The distances are too vast, the times too long, the energies too great. This is not a failure of will or technology. It is a fundamental feature of the universe we inhabit. The cosmos is built on a scale that dwarfs human existence. We evolved to navigate savannas and forests, to comprehend distances measured in days of walking. Our brains are not equipped to intuitively grasp light years and millennia, and yet we have grasped them. Through mathematics and observation, through the patient accumulation of knowledge across generations, we have come to understand our place in a galaxy that spans 100,000 light years. We know how big it is. We know what it contains. We know how long it would take to escape. That understanding is itself a form of exploration. We have traveled in mind where our bodies can never go. We have extended our knowledge across distances that our physical forms cannot cross. The astronomer who measures the distance to a globular cluster has, in a sense, visited it. The physicist who calculates the trajectory of a hypervelocity star has traced its path across the galaxy. The entirety of our cosmic knowledge is a kind of exploration, conducted with photons and mathematics, rather than spacecraft and footprints. Every night, weather permitting, you can look up and see the Milky Way stretching across the sky. From a dark location, far from city lights, it appears as a band of pale light arching from horizon to horizon. This is what Galileo first resolved into individual stars more than 4 centuries ago. That pale band contains everything I have described in this script. The spiral arms winding outward from the central bar, the globular clusters orbiting in their ancient halo, the dark molecular clouds where new stars are being born, the supermassive black hole lurking at the center, the dark matter envelope extending far beyond what any telescope can see. When you look at the Milky Way, you are seeing light that has traveled for thousands of years to reach your eyes. The stars of the central bulge, visible as a slight brightening towards Sagittarius, emitted the light you see when Rome was a republic and China was ruled by the Han Dynasty. The more distant halo stars sent their light when woolly mammoths still walked the earth. You are seeing the past. Everyone who looks at the sky is looking at the past. Light is not instantaneous. It takes time to travel from source to observer. The farther away something is, the farther back in time you are seeing it. And here is the profound part. You are not just seeing the past. You are part of the past. The atoms in your body were forged in the cores of stars that lived and died billions of years ago. Carbon, oxygen, nitrogen, iron, all the elements heavier than hydrogen and helium were synthesized in stellar furnaces or supernova explosions and scattered into space, eventually coalescing into the molecular cloud that became our solar system. You are made of the Milky Way. You are the Milky Way. Briefly aware of itself. A piece of the galaxy that has developed the capacity to measure the galaxy, to calculate how long it would take to escape, to contemplate its own cosmic insignificance with something approaching understanding. At light speed, the fastest anything can travel. Escaping the galactic disk takes 1,000 years minimum if you go perpendicular to the plane. Reaching the galactic center or outer rim takes 26,000 years. Crossing the dark matter halo to truly escape takes nearly 1,000,000 years. These numbers exceed human timescales by orders of magnitude. 1,000 years is longer than most empires have lasted. 26,000 years exceeds the entire history of civilization. 1,000,000 years is longer than Homo sapiens has existed as a species. Time dilation offers a peculiar escape. A traveler moving at 99.99% of light speed would experience the journey to the galactic center as lasting only a few centuries. But they would pay for that compressed experience with everything they left behind. They would become emigrants, not just in space, but in time, permanently displaced into a future they cannot share with anyone from their past. The Milky Way is not a prison exactly. It is more like an island in an ocean so vast that the far shores can never be reached. We can see distant galaxies through our telescopes, billions of light years away. We can measure their distances, analyze their compositions, trace their evolution, but we can never visit them. The space between us expands faster than any spacecraft could cross. This is not a poetic exaggeration. It is a measurable fact. The Hubble constant tells us that distant galaxies recede from us at speeds proportional to their distance. A galaxy 100 megaparsecs away recedes at about 7,000 kilometers per second. A galaxy 1 gigaparsec away recedes at about 70,000 kilometers per second. Beyond a certain distance, called the Hubble sphere, galaxies recede faster than the speed of light. This does not violate relativity. The galaxies are not moving through space faster than light. Space itself is expanding, carrying them away. And there is no limit to how fast space can expand. The cosmic horizon, the boundary beyond which we cannot ever communicate even in principle, lies at a co-moving distance of about 14 billion light years in every direction. Galaxies beyond that horizon are lost to us forever. In the deep future, trillions of years from now, this isolation will become absolute. The accelerating expansion of the universe will carry distant galaxies beyond our cosmic horizon, one by one, until nothing remains visible except the merged remnant of the Milky Way and its local group neighbors. Our descendants, if any exist, will look up at a sky with far fewer galaxies, eventually just one. The universe will appear to shrink as the expansion carries its contents beyond reach. But that is a problem for beings who do not yet exist. In a future so remote, the speculation about it borders on fantasy. For now, we have a galaxy to contemplate. 100,000 light years of stars and gas and dust, nebulae and clusters and black holes, all of it bound together by gravity into a structure that has persisted for 13 billion years. We are inside it. We are made of it. We will never leave it. To escape the Milky Way at light speed would take 1,000 years at minimum, nearly 1,000,000 years at maximum. No human has ever made such a journey. No human ever will. But we have looked upon our galaxy and understood it. We have measured its dimensions without leaving our planet. We have traced its history through fossils of light billions of years old. We have asked how long it would take to escape and answered the question with precision. The Milky Way stretches above us, a river of ancient light. We are inside it. We are made of it. We will never leave it. And somehow, knowing what it is, knowing how vast it is, knowing how long it would take to escape, that is enough. That knowledge is itself a kind of transcendence. We are small and mortal and bound to one fragile world orbiting one ordinary star. But we have comprehended the galaxy that contains us. We have reached across 100,000 light years with our understanding, if not our bodies. Consider what that means. We are a species that evolved to survive on African savannas, our brains optimized for tracking prey and remembering water sources and navigating social relationships within small tribal groups. Nothing in our evolutionary history prepared us to contemplate distances measured in light years or times measured in millions of years. And yet we do contemplate them. We have developed mathematics capable of describing curved spacetime and quantum mechanics and the behavior of matter at the cores of stars. We have built telescopes that can detect the light from galaxies billions of light years away, photons that have been traveling since before the Earth existed. We have launched spacecraft that have left the solar system and continue outward even now. We are extraordinary in our way, not because we are at the center of anything, which we are not because we are large or powerful or long-lived, which we are not, but because we are aware. We know where we are. We know what contains us. We know how long it would take to leave. That is the strange gift of consciousness. We cannot escape the Milky Way, but we can know it. And in knowing it, we participate in something larger than ourselves, something that will continue long after we are gone. The stars will keep burning, the galaxy will keep turning, and somewhere, perhaps, other minds will look up at the same pale river of light and ask the same questions we have asked. How big is it? How far does it extend? How long would it take to escape? The answers, when they come, will be the same as ours. Very big, very far, a very long time. And that too is a kind of connection, a shared understanding across distances and perhaps across species. The Milky Way is vast and indifferent, but it has produced beings capable of wondering about it. That wonder is not nothing. That wonder is, perhaps, the most remarkable thing the galaxy has ever done. We are bound to this island of stars. We will never leave it. But we have understood it. That is both the limit and the wonder of our existence. We are prisoners of the Milky Way, and somehow that is enough.